Hello students, today we will be talking about MOT, that is molecular orbital theory. In this theory, we will be discussing about bond order, stability of molecules, their existence, their magnetic behavior, their electronic configuration, all these things we will be discussing in MOT. Now the question is, before MOT we talked about VBT. When already we discussed formation of molecules in VBT, then what's the need of MOT? Why do we discuss MOT? There were many points which VBT cannot explain, but we can get the answers in MOT. Now what are those points? How MOT is different from VBT? Let us discuss about this. According to VBT, whenever two atomic orbitals overlap, now what is the condition for overlapping? You must be remembering half-filled atomic orbitals having opposite spin electrons. They overlap. Such as, if you take the example of hydrogen molecule. According to this hydrogen atomic orbital 1s1, second 1s1 opposite spin. These two overlap, resulting into H2 molecule. By their overlapping of these two atomic orbitals, we get hydrogen molecule. Clear, children? Now, what MOT says? According to MOT, whenever two atomic orbitals, let us again take hydrogen. These are two atomic orbitals of hydrogen or any other atom. When these atomic orbitals, they combine together, it doesn't talk about overlapping. There is no meaning of overlapping here. This theory says when these atomic orbitals, they combine together, they give us two new molecular orbitals. Absolutely different concept. We will be getting two new molecular orbitals. This concept of molecular orbital was missing in VBT. VBT is absolutely silent regarding molecular orbitals. So, we doesn't get any information of molecular orbitals in VBT. This was the first point of difference. Now, what is the next point of difference in VBT and MOT? How MOT is better than VBT? Right? We are not saying that VBT is not useful. VBT is also a useful theory, but there were some drawbacks due to which we need MOT. Now, what is the next one? In MOT, we get the exact information about magnetic properties of a molecule. I'm not saying that VBT doesn't talk about magnetic properties. Yeah, to some extent we get information about magnetic properties, but there were some problems also. Like, if we take the example of oxygen molecule, according to VBT, O2 is a diamagnetic molecule. Now children, what do we mean by diamagnetism? Diamagnetic substances are the substances which are weakly repelled by external magnetic field. Got it? They are repelled by external magnetic field. But experimentally it is proved that oxygen is not diamagnetic. Actually, this is a paramagnetic substance. Paramagnetic, just opposite to this. Now you can easily guess. Paramagnetism means which are attracted by external magnetic field. And experimentally it is proved that oxygen is a paramagnetic molecule. This paramagnetism of oxygen is explained by MOT but not by VBT. This we will be discussing in detail in this unit only, but here we are only talking about some very basic points of comparison of VBT and MOT. Got it? Next, whenever we talk about bonding in VBT, according to VBT, they can be a single bond, they can be a double bond, or they can be a triple bond between two atoms. Got it? But here there is a very interesting feature of MOT. MOT says bonds can be in fractions even. Have you ever heard about this? No. Fractional bonds. This we talk in MOT. According to MOT, it can be 1.5. It can be 2.5. Interesting, no? But this thing is absolutely missing in VBT. It can be 0.5 even, bond order, which we never discuss in VBT. Got it? Next, MOT also talks about wave mechanics. In atomic structure unit, we read about Schrodinger's wave equation. That what do we mean by atomic orbitals? Orbitals means probability waves. Right now, the space, 3D space around nucleus where probability of finding the electron is maximum. So this wave mechanics concept is completely missing in VBT. It never talks about wave mechanics. Yeah, children, I think this is clear. Next, this was one point of difference. This was another point of difference. Before this, we talk about molecular orbitals. That was also missing in VBT. Now, one more thing is VBT is again silent about comparative stability of molecules. Comparative stability. But here we get the information about comparative stability. What do I mean by comparative stability? Suppose I have to compare stability of two molecules. For example, I want to compare the stability of H2. Its cation, its anion. I cannot compare this in VBT. No chance. But here in MOT, I can compare their relative stability. Yeah, children, I think now all these parameters are absolutely clear to you. That how VBT doesn't give few informations which we will be getting by using MOT. This was a very brief comparison of VBT and MOT. Now we will be talking about MOT in detail because we are leaving VBT here because we have already talked about VBT in our previous lectures. Now in MOT, initially we will be having two terms. These two terms are atomic orbitals and molecular orbitals. Now what do we mean by these two terms? Atomic orbitals belongs to atoms. They belongs to atoms. Molecular orbitals belongs to molecules. Correct? Then coming to their symbols. Symbols of atomic orbitals you all must be remembering. These are S, P, D, F. These are the representations now. Now, what would be the symbols of molecular orbitals? Let me tell you. These are sigma, pi, delta. In this unit, we will be discussing about sigma molecular orbital, pi molecular orbital, but we will not be talking about del molecular orbital because this is not a part of our curriculum. Got it? Now coming to the types of molecular orbitals. And how many molecular orbitals do we get by these atomic orbitals? Number of molecular orbital is exactly equal to the number of combining atomic orbitals. Like if two atomic orbitals are combining by two atomic, suppose these are the two atomic orbitals. Got it? By combining these two atomic orbitals, we will be getting two new molecular orbitals. These are the two new molecular orbitals. Got it? Now, how do we designate them? What's the basic difference between these molecular orbitals? These two molecular orbitals, out of these two, the one is bonding molecular orbital and the second one is anti-bonding molecular orbital. Bonding we will be representing by sigma, pi. Anti-bonding like sigma star, pi star. Now the question comes to your mind. Can I just reverse it? Means, can I write here anti-bonding and here bonding? No, my dear children, not at all. Why? Because bonding molecular orbital, they have low in energy. This is lower energy and this is the process of increasing order of energy. Anti-bonding always has more energy as compared to bonding. That's why the orbital at higher level is anti-bonding, at lower level is bonding. Now again next question, which would be more stable? Can you tell me? More energy means more stability or less stability. A very confusing part right now. But again, very simple explanation. The laws of chemistry are absolutely related with nature. How? Suppose if you're not getting food for 3, 4, 5 days, how do you feel? Low in energy or high in energy? Your movements are going to slower. Clear now? So it means the orbital with low energy is more stable or less stable. Now you can easily answer me. Lesser is energy, lesser is stability. So bonding, as it is less in energy, so this is more stable or less stable? Less energy means more stable. More stable because lower is the energy level. You can't walk properly, you can't do your work if you are feeling low in energy. But if you are fully energetic, you can easily do your work. You can go to play, you can study. Well, means whatever you want, you can easily do if your energy level is high. Means high energy level is leading towards less stability or towards movement. Got it? So, as it has high energy, so less stable. Yes, my dear children. I think now this concept of bonding, anti-bonding along with their stability is clear to you all. Yes or no? Yes? Now, we will be talking about their formation. This was only a brief introduction of two types of molecular orbitals, bonding and anti-bonding. Now we will be talking about their formation, that how these orbitals, bonding as well as anti-bonding, are formed. First, what are the conditions for atomic orbitals to combine so that they form atomic orbitals to combine so that we will be getting molecular orbitals? The very basic conditions are, the first of all, atomic orbitals with same energy, or we can say almost same. Almost same. This was the one condition. Now, what would be the second condition for their combination? The second is symmetry. Right? Atomic orbitals, same symmetry, same energy or almost same energy. They combine, giving us molecular orbital. Now, same and almost same. How can we tell about this? Same energy word we can use when the molecule is formed by same type of atoms, like H2 molecule formed by two hydrogen atoms. So 1s can combine with 1s because they have same in energy, but 1s cannot combine with 2s. 2s can combine with 2s, but not with 2p. Got it? Almost same. This word we will be using for heteronuclear molecules. Means the molecules which are formed by two different atoms. Like, if we will be talking about combination of carbon and oxygen. Carbon and oxygen combined giving us carbon monoxide. Now, if we take 1s of carbon and 1s of oxygen, of course their energies would be slightly different. There would be no major difference in their energies. But yeah, somewhat energy difference is present. So for such kind of cases, we will be talking about almost same energy. Right children? I think now this is clear. Now we will be talking about their shapes. If we have p atomic orbital, in p you know we are having three orbitals. These are px, py and pz. Now children, can you tell me that px can combine with py? Yes or no? I think now you can easily give me answer on the basis of this point that there is no chance of combination of px with py. Got it now? So this is the meaning by symmetry. Px can combine with px, py with py, similarly pz with pz. Yes, now this point is also clear to all of you that what are the main conditions for atomic orbitals which are required so that we get effective combination of atomic orbitals to get the molecular orbitals. Now again, how these bonding molecular orbitals and anti-bonding molecular orbitals are formed. We will be talking about this thing now. Now everyone knows what do we mean by bonding molecular orbitals. Still I am repeating children, bonding molecular orbitals low in energy. Low in energy means more stable. More stable. Representation sigma, pi, and we will be not talking about then molecular orbital because we don't need that. Now, how these are formed? When we get molecular bonding molecular orbital and when do we get anti-bonding molecular orbital? Let us talk about electronic beams. moving towards wave mechanics given by Schrödinger. You must have read about Schrödinger's wave equation in atomic structure unit. Got it now? So how these wave functions are represented? What would be their symbol? Xi. Remember now? What is the orbital? This is simply probability of finding electron where it is maximum, or electronic waves. Got it? So let us we have these two atomic orbitals now, which will be giving us molecular orbitals. This is first, we may write Xi1, second we may write Xi2. So let us you have these two electronic wave. This is first one and this is second electronic wave. Now when these two electronic waves combines, we call it interference of waves. This interference can be constructive or it can be destructive. Clear? If these two are, I am giving here plus sign. If these two electronic waves, they are combining together, this is constructive interference. Constructive interference. As a result of constructive interference, resulting molecular orbitals, simply these waves are going to be added up and you will be getting this is. And this resulting wave function gives us bonding molecular orbital. Yes children, clear the result of constructive interference? Now we will be talking about another case where these two wave functions are going to cancel out each other. And when they cancel out each other, in that case, this is a type of destructive interference. Got it? Means Xi1 minus Xi2. Like these two waves. This is first one and then we have the second wave. Now, as they cancel out each other, so what is left us? Nothing. We will be getting nothing because they cancel out each other. So here this is termed as destructive interference. And as a result of destructive interference, you will be getting anti-bonding molecular orbital. So whenever the wave functions are going to add with each other, we will be getting bonding molecular orbital. And whenever they cancel each other, means destructive interference, and as a result of destructive interference, you will be getting anti-bonding molecular orbital. Yes, now this concept of bonding, anti-bonding is clear to you. Now in next video, we will be talking about formation of sigma and pi molecular orbital, how these orbitals are going to be formed. To understand all these things, you need to be absolutely clear regarding these all basic concepts of molecular orbital theory. I hope now you understood all these things. Till that, revise all these things so that you can easily understand our next topic.